And Alan will be talking about sensitivity analysis for forward and inverse uncertainty quantification. So Alan, you're up.
Let me go ahead and share and enter full screen. All right, should we get going?
Yep.
Okay, hi. Okay, let me go ahead and minimize this. All right, let me just get to it. Once this works, okay. So we already saw one talking sensitivity analysis. Let me just start by some broad comments. Basic idea is you have a model, f of theta. Typically, for what we do, evaluating f of theta requires solving some differential equations or ODEs, PDEs, DAEs, stochastic models. And theta denotes a vector of uncertain model parameters. Broadly speaking, global sensitivity analysis tries to find entries of theta that are quote unquote most important to model output. Of course, that I put that in quotes because that has to be defined, how you want to characterize most important. There are many ways. We saw some in the previous talk. So you have variance-based methods, derivative-based methods, moment-independent methods, so on and so forth. A question, why do you do global sensitivity analysis? What are some of the motivations? Well, for one thing, if you have a very complicated, complex physics system, and it has a lot of unknown, uncertain parameters, you wonder if you figure out which are the parameters that are most important, then you understand the model better, so that's helpful. From computational point of view, you could possibly reduce the dimensionality of the input parameter. That can help you with common uncertain quantification tasks like forward EQ, solving inverse problems. And more broadly, maybe you can use global sensitivity analysis to simplify the model. Now, that's an interesting research question. We can discuss that. But these are some of the basic motivations. Some standard global sensitivity analysis measures. So here I consider a scalar valued output. Thierry mentioned the Sobol indices, where you characterize the importance of variable by looking at this conditional expectation and look at the variance of the conditional expectation conditioned on the ith input and see what proportion of the variance that's responsible for. That's one way. So these are the so-called first order Sobol indices. You can define total order, joint indices, so on and so forth. Estimation of these indices typically is expensive, requires some form of sampling, as Thierry mentioned in the previous talk as well. You can also look at the derivative, and since the parameters are uncertain, you can look at certain moments of the partial derivatives. And again, you can generalize this stuff for vectorial outputs, functional outputs. And there are other metrics, of course. We saw some in the previous talk, moment-independent measures, Morris screening, activity scores, where you leverage ideas from active subspaces, and so on. Okay. So what are some of the challenges / opportunities? Well, in some cases, you might have very high dimensional parameters, so that performing sensitivity analysis is very helpful, but also expensive because you have to explore a high dimensional space. F could be very expensive to evaluate. It could be a high fidelity model of complex system. Entries of theta might be correlated. There were some comments in the code. So if you assume independence, for one thing, that's probably not the correct thing to do. And also, you might have difficulties even computing them. The result of sensitivity analysis depends on how you model the uncertainty in the parameters. So there's an interesting question of how sensitive is your sensitivity analysis to the input distribution. So these are the robustness issues. Pierre has done quite a bit of work on that. So you can enjoy and ask them. Your F might be time dependent signal, or it's a spatially distributed function. So you have to define suitable indices, and also you have to work with a high dimensional output potentially. You could also have stochastic models where there is parametric uncertainty, but you're also working with a stochastic simulator. So there's some intrinsic randomness in the model. such as stochastic compartment model, chemical systems, which we will discuss in a minute, stochastically forced dynamical systems, and so on. A lot of interesting situation arises where you work with multi-scale problems, where problems are defined in different scales. And the interesting question is how you can leverage information from like, coarser scales to inform the more finer microstructural models. What I will talk about in this talk is two topics, multi-scale global sensitivity analysis, and also have a lot of interest in inverse problem, and this bridges the fields sensitivity analysis for inverse problem. So we'll get to that later in the talk. All right. So the first topic is this global sensitivity analysis across different scales with application to stochastic chemical systems. This joint work with Pierre Grimaud and Mike Merritt. In fact, Mike was the lead author in this article that's under revision. You can find the preprints in arXiv. All the numerical results that I'll show were generated by Mike. So you can talk to him as well. All right, so I want to talk about sensitivity analysis for stochastic chemical systems and across scales. So I have to give you a little bit of background on it. Not too much, we'll just cover the basics. The situation is as follows. I have n chemically reacting species. And the state vector that I consider is X, is each component of X indicates the number of molecules of the ith species at a given time. So I have M reactions. Each reaction has a stoichiometric or state change vector that tells you what happens if the jth reaction happens. How does the state vector change? You have a reaction rate for each reaction, and a propensity function. So these propensity functions define, as I wrote in this here, the probability that jth reaction occurs at the infinitesimal time interval. A simple example. Let's consider a two species model. So S1 gets converted to S2 with some rate K1, and S2 gets converted back to S1. So in this case, the propensity function for the first reaction is A1 is K1 X1, you can show that. And the corresponding state change vector is mu1. It's just minus 1 and 1. You lose one of molecule of S1 and gain one molecule of S2. And you can define similarly for this case, it's the same a situation for the second reaction. So you can define that. All right. So what are the scales here? We can consider model in the microscale where I track the number of molecules of each species over time. So here X is going to be the stochastic process, takes integer values. Non-negative integers. You can simulate the stochastic system. There are algorithms for it: stochastic simulation algorithm, next reaction method, random chain change. There are different algorithms. You can consider an approximation to the stochastic model provided by this mesoscale model. For example, the chemical Langevin equation, where you use a real-valued stochastic process. And you have to solve some SDEs, stochastic differential equations. At the macro scale level, you track the species concentrations using a system of ordinary differential equations. Now that macro scale model here is going to be a deterministic model. And we'll see a little bit more about it in a minute. So these are the different scales that I consider here. To motivate discussion, what I will do, I'll consider a specific system, a simple but important reaction mechanism from enzyme kinetics. We'll present some numerical results we'll discuss. So here the situation is as follows. You have a substrate that binds to the enzyme binds to the substrate and results in a complex species that has rate K1. This C can break down and give you what you started with, S and E, substrate and the enzyme, or it can break down and give you the product, P, and the enzyme. So these are the species. That's what this is the story of the system. The uncertainty we consider are in the reaction rates. So we have three parameters here in this problem. And here for this test, we consider the quantity of interest to be the time average of the product, the concentration of the product. And we can compute the concentration obviously by normalizing by the system volume in the stochastic case. And we would like to ask the following question. Can we use the macro scale model for efficient global sensitivity analysis of the micro scale model? So that's the overarching question here. Let's take a look at some nice plots. So here I simulated the system. I'm showing some realizations of the trajectory. They're different because it's a stochastic model. So if I run the same code even with the same parameter multiple times, I get different realizations. And you see the conversion of the substrate, the red ones, to the product as a function of time. These are molar concentrations. Okay. And I could also consider the macro scale model so that's deterministic. That's given by the solution of the reaction rate equations. And there's rigorous theory linking these two scales, the macro scale and the micro scale. We'll discuss a little bit in a minute. So what's the global sensitivity across scale? What's the question that we want to address? So I have a stochastic model or quantity of interest is F, and I can perform global sensitivity analysis on it. Let's say I compute Sobol indices. In this case, I will get, so the Sobol indices will be random variables, and I can consider a limiting process and get some deterministic indices, or I can consider some limiting process, and that we will discuss what that is in this case, and get the deterministic model and perform global sensitivity analysis on the deterministic model. We get deterministic indices. And the question, does this diagram commute? In what sense? What assumptions are needed? Now, in this talk, I will not go over the theory too much. I will illustrate numerically, but you can look at our article for the theoretical details. All right, so let's have one slide. What's the relation between the stochastic model and the corresponding deterministic one in this chemical system setting. So I can define the system size as the Avogadro's number times the system volume. And this complicated looking formula here, you don't have to necessarily understand. It will take some time. It requires some background in this area, but this gives you a stochastic process. With stochasticity come from this YJs. These are the so-called, these are unit range Poisson processes. And this A tilde, these are the propensity functions, but I've modified them because here we are considering the concentrations, because I want to be able to compare the stochastic model to the deterministic one. So the deterministic model gives you concentrations. So we also consider the corresponding concentrations from the stochastic model. And the thermodynamic limit in this case is the limit as the system size goes to infinity, gets very large. So there's a theorem, I can give references, I didn't put anything there, but one can prove almost sure convergence of the stochastic trajectory to the deterministic one. And where this Y, the deterministic solution, satisfy the so-called reaction rate equation. That's the macro scale model. It's an ODE system that you can write the form of. You can integrate it with some Runge-Kutta or something. And so what's the stochastic quantity of interest? We can consider, let's say, one component of the stochastic model, take some time average or something so we can get a scalar observable out of it. And the corresponding deterministic quantity of interest is computed based on the reaction rate equations. So the idea would be to perform sensitivity analysis on this F tilde and say something meaningful about the sensitivity of this F, the stochastic F. All right. So let's do it. Let's back to this Michaelis-Menten. I just wrote it in one line here, the system. And I remind you of the quantity of interest that we considered. So what I'm looking at here is the convergence of the so-called total Sobol indices. I didn't define the total Sobol index earlier, but it's related to the first order indices. And what I've plotted, this red dashed line, is the index I get based on the reaction rate equations, and the blue line so that blue line is the mean of the corresponding stochastic Sobol index, and the bounds are the fifth. The error bars correspond to the 5th and 95th percentiles. Because we have a distribution for the stochastic index. And as you see, as the system size grows, then the stochastic indices do seem to converge to the deterministic ones. The plot to the right shows the histogram, where I track the histogram of the stochastic Sobol index as the system size grows. And you see that this PDFs or the histograms concentrate towards a limit, and that corresponds to the index that you get from the RREs. Okay. We can repeat the same exercise for the sensitivity with respect to the second reaction rate. So that one was for K1, this is for K2. And similar observation as before. Take notice of the scale of the y-axis in the left plot. So this already indicates that this one is about 0.3. This one is much smaller. And we can do the same thing for the third parameter. I'm just waiting until the ambulance goes away. All right. We also applied this to a more complicated reaction system. We don't need to necessarily go through the reaction mechanism. That's a so-called genetic oscillator network. We have 16 reaction rates, and the quantity of interest is the time average of the repressor protein R. Try to highlight it in this reaction mechanism. We don't necessarily need to concern about the details of the system. One thing I would mention, this is actually quite expensive to simulate. The stochastic model is quite expensive to simulate. It takes a lot of time. So trying to do sensitivity analysis on the stochastic model directly could be quite expensive. So we performed global sensitivity analysis on the corresponding reaction rate equations. And again, so there's a lot of parameters, but one thing that you immediately notice is that in the middle, we have the 6 reactions that looks like the total Sobol index is small compared to the other ones. So let's test. I mean, it's an illustration of getting meaningful information from this macrostructural model about the stochastic model. So here I'm looking at the distribution of the quantity of interest. Okay, so the blue line, the solid line, corresponds to the distribution of the quantity of interest if you don't fix any of the parameters. And take notice, here we are sampling the quantity of interest in a product space because there's the uncertainty coming from the parameters, but then the model itself is stochastic. So we have to sample in the product space. If I fix the parameters based on the Sobol indices that I got from the deterministic model, that corresponds to this, the red one, where the indices are less than some tolerance, I see that I can capture the distribution of the stochastic quantity of interest well. So that already numerically also indicates that this is successful in terms of parameter dimension reduction here. But another thing we're showing here is that if you go ahead and reduce parameters too aggressively, then you will get this other line where you see, obviously, you're underestimating the variance a little bit. And this black dashed line indicates that, oh, if you do the wrong thing, what will happen? So here we are fixed actually the most important parameters, and obviously you're getting a distribution that is far from the correct distribution of the stochastic quantity. So for this part, let me just make some comments so we can use the reaction rate equations for efficient global sensitivity analysis of stochastic chemical system. We have done some numerical illustration on biochemical reaction networks. You can look at our article. And also we have done the theoretical analysis of convergence. We proved the almost sure convergence for the stochastic Sobol indices to the deterministic ones. We could discuss maybe after the talk. What are some things to look into? Specifically, these chemical systems, an interesting question that came up from the review comments in the article was, what's the rate of convergence of the stochastic Sobol indices as the system size grows? It's interesting. One could consider different global sensitivity analysis measures across the scales. For example, some of the ones that Thierry showed earlier. Or you could also consider other intermediate scales. So here we looked at two extremes. We looked at the fully stochastic system and went all the way to the thermodynamic limit. So one could also consider the mesoscale models like chemical Langevin equation and see what's the relation of the indices that you get from that to the other scales. More broadly, we can consider global sensitivity across scales or fidelities in various contexts. For example, interesting example is the homogenization of PDEs, where you can define a effective set of PDEs that describe this physics, where you also have a microstructural model where you have rapidly oscillating coefficients there. Again, the question is, can I use the effective upscaled equations for informed global sensitivity analysis on the stochastic, or not necessarily even stochastic, but more complicated PDEs. We can do multi-level Monte Carlo type algorithms where here the scale is defined by the discretization. So if I can leverage information from coarser discretizations on the to do some accurate and efficient global sensitivity analysis. There's some work out there about this, but we're looking into it here at NC State also. And multi-fidelity models. So sometimes you define models at different fidelities and you want to see, again, how can I combine information coming from across models with different fidelities to do efficient global sensitivity analysis. So this is the first part of the talk. Then we can discuss sensitivity analysis of inverse problems. Now, the work I'll present is, we have an article in inverse problems, just got accepted. Lead author is Isaac, graduate student at NC State. Collaborators are Joey and Bart. So let's get to it. So we call this the hyper-differential sensitivity analysis. And why hyper? You can think of this, the sensitivity analysis with respect to hyperparameters. So what is the goal? Determine the sensitivity of the solution of a deterministic inverse problem to perturbations of additional model parameters or data measurements. So what are the additional model parameters? So when you solve the inverse problem, we will discuss in a minute, you're trying to estimate some parameter of interest, but there are other parameters in the model, in the governing equations that maybe you are not necessarily interested in estimating, but you still have to specify them based on prior knowledge or expert opinion or historic data or whatnot. So you want to see how sensitive is your inverse problem to those parameters. Why? Why do you do a sensitivity analysis of an inverse problem? Well, you understand the problem better. Also, doing sensitivity analysis with respect to data could guide or augment design of experiments. If I find the inverse problem is very sensitive to some measurements, then it's a good indication those are useful measurements. If not, then maybe I don't necessarily need to record those measurements. So what's an inverse problem? Remember, or let's note, in an inverse problem, I have a computational model and data. And the goal is to estimate a parameter M is the inversion parameter. It could be a scalar, vector, or a function. In what I do usually, it's a function. So you want to find a parameter that such that the output of your computational model is close to the measured data. And we have various parameters here. We use color coding to make it a little bit easier. So you have experimental parameters that specify your experimental conditions. You have the auxiliary parameters, that these are parameters in your governing model. And here abstractly, I denoted the governing model by this R. We'll have a specific example in a minute. And of course, we have to deal with ill-posedness. So I have considered a regularization operator. I just put it there abstractly. And here, U is the state variable. And since we have a lot of different parameters, so I call M the inversion parameter, take experimental parameters and auxiliary parameters, we lump them together, we call them complementary parameters. All right. So you give me the complementary parameters, the auxiliary parameters, the problem data, measurements, I can solve the inverse problem and I get a local minimizer at that point. And I can consider the optimality condition. This first order optimality condition is the derivative equal to 0. And here we are using essentially implicit function theorem. And we can differentiate through this optimality conditions. And once you work it out, you get this equation for this derivative operator. That's the sensitivity operator of the solution of the inverse problem to theta. And this the inversion times the B, where, so yeah, H is the Hessian. B is this operator with corresponding to the mixed derivatives. That's the derivative of the gradient with respect to theta. And obviously for large scale applications, you have to rely on adjoint state methods for gradient and Hessian computations, definitely gradient computation. And of course, yeah, this D measures the change of the solution of the inverse problem where the nominal parameter values are perturbed in a given direction. All right. And of course, this is a complicated operator, this D. We can use this D to define sensitivity indices. I'll be, I'm not going into too much details, but I will show you some results to motivate and give intuition. So here's the inverse problem we considered. It's a transport of a contaminant, or not necessarily contaminant, some tracer in a geological formation, single phase flow. The first PD is the pressure equation. The second one describes the transport. C is the concentration. And the goal is to estimate the log of the permeability field using measurements of the pressure and concentration. And of course, you have different parameters in this model. You have the source term for the transport equation. You have the boundary conditions for the pressure equation. You have the diffusion constant in the transport equation. These are the ones that we considered in our numerical experiments. So this is the inverse problem. As I said, we take measurements of pressure and concentration. So therefore, we have two data misfit terms. And there's the regularization operator. And where this optimization problem is constrained by this governing equation. So, okay, here's the result of solving the inverse problem. Okay, yeah, we can solve the inverse problem. So this is the truth log permeability field that we assumed, and this is our reconstruction of it. And maybe I will show you these results, and then possibly we can go to discussion. Well, do we have time? So we can do a little bit more. So these are the so-called generalized sensitivities that we define based on the derivative, where I look at the sensitivity to experimental parameters. So these are global type sensitivity, not global sensitivity, and this is still local because we take derivative, but they give you overall picture. So in this case, the concentration measurements were more important. And if you look at the auxiliary parameters, the source term and the concentration equation showed some sensitivity. So that That was important. Diffusion constant, not surprisingly, the inverse problem solution is not that sensitive to it. Again, intuitively, this makes sense that the boundary conditions in the pressure equation were important. The inverse problem solution is highly sensitive to them because they essentially, the boundary conditions on the pressure equations drive the flow. So the result is very intuitive. We can do sensitivity analysis with respect to data measurements. This plot maybe a little bit will take some time to explain. So let me just go to, maybe just as an illustration. Let's discuss the sensitivity of the sensor to sensor data coming from the to concentration data coming from the sensors. So we have a grid of sensors, and that's why we have this grid of plots. And the x-axis in each of these plots is time. And we see that we observe some sensitivities to some of these sensor measurements over time. So that indicates those observations are important. And then we see very little sensitivity to sensor data coming from some other sensors, which possibly indicates those sensors are probably not very useful. You don't necessarily need to take those measurements. So, but this is a type of insight that this hyper-differential sensitivity analysis can provide on a inverse problem. And we have also done sensitivity analysis with respect to pressure data. This is, again, we can discuss details and interpretation and so on, but we have that information too. Notice that the pressure is not time dependent, so I just take the sensitivities for each sensor. This is each one of these dots corresponds to a sensor where we take measurements, and the color indicates the magnitude of the sensitivity. All right. So in summary, hyper-differential sensitivity analysis, HDSA, helps to understand sensitivity of the inverse problem solution to auxiliary parameters. These are parameters and governing PDs that you're not necessarily estimating. In fact, this in some cases, it could even tell you, if you have the data, it might be helpful to actually try to estimate some of those auxiliary parameters if you observe high sensitivities to them. You can understand sensitivity of the inverse problem solution to different measurements, different sensors, and also measurement types. So as such, this does augment design of experiments. You can identify important measurements by doing this type of sensitivity analysis. And I'll be happy to discuss more about that because I also do research on design of experiments for inverse problems. And what are some of the interesting things that we can discuss? And again, this is talk on the global sensitivity analysis, but I understand we have a inverse problem working group also, so this could breed some interests. So some of the interesting questions, hyper-differential sensitivity analysis for Bayesian inverse problems. So what we have considered so far is deterministic inverse problems. So Isaac, my student, who led this initial paper, is working on that now. We can do global HDSA. So what I did was a local sensitivity analysis. In fact, with local in the space of the complementary parameters. So there may be some low-hanging fruits there for doing global hyper-differential sensitivity analysis. Hessian preconditioning ideas. If you remember, the derivative operator involves Hessian solves, which is essentially what you do when you do a Newton step, you know, when you solve the inverse problem. So any preconditioning ideas that you have for that could be useful here, and one can explore more. The last two bullets are essentially, these are things that came up with discussions I've had recently with Joey, and he has been working on, Joey Hart, who has been working on this stuff, impact of ill conditioning of the Hessian on HDSA. And if you want to do sampling in the joint space of the parameters and the inversion parameters and also some of the auxiliary parameters, then the HDSA could be helpful for that as well. Again, this is, you can talk to Joey really because that's the type of things he does these days. But I'm gonna stop there.
Thank you very much, Alen. So let's see, we again, have plenty of time for questions. So we'll proceed as we did before. So either raise your hand or you can type something in the chat, rather, if you have questions for Alen.
Yeah, I don't see the chat, so somebody has to read them for me.
I think Mansur will do that for us.
I'll read them if they come up there. So I
had a quick.
Yeah, go ahead. Sorry, go ahead. Go ahead, David.
Well, I wanted your thoughts on how to proceed in a situation where you don't have a well-specified model, where you might be working with, say, an agent-based model, and you'd like to be able to express the sensitivity of the results of an agent-based model to the parameters that drive the agent's behavior.
Okay, so that's more like doing into the realm of forward UQ. Right, so doing the derivative-based approach probably won't work necessarily because you might not have that type of regularity, but I would start looking into a variance-based type approach. Some of the things that Thierry also mentioned, it's more generalized sensitivity indices. I would look in that direction.
Thank you very much.
No problem.
So maybe I'll add a question in here, Alen, which is more of a clarification.
Yes.
You go to the Michaelis-Menten slide in part 1. So you talked about stochasticity before that, but when you were, with the here, right, with the QOI, when you did the average product concentration. So, you're running the Michaelis-Menten model as ODEs from the law of mass action. Where does omega come into the forward model?
Okay. Let me just go to it. So when you actually simulate the stochastic system, you're not doing the mass action thing. There's a stochastic model corresponding to that you can define. Yeah.
So that was in your commuting diagram. That was.
Yeah.
So there's the lower part, and you have a different thing for the upper part.
I can give an intuitive idea, but how would you simulate that? If you're using the so-called stochastic simulation algorithm, at every, let's say, point in time, you have to determine what's the next reaction that's going to fire, and that is random. And also, let me just make this full screen. So you have to determine what is the next reaction that's going to fire, and at what time, and those are random. So that's why you get this type of realizations for the system.
So you only have one reaction firing at any given time?
So, right.
Is that a problem, though? They're kind of viewed as occurring simultaneously chemically, right?
So that's why you look at infinitesimal, this small time interval. So, okay, what's the next reaction that's going to fire? Because at a single instant in time, you say, okay, one reaction is going to happen in this really small time interval.
Right. All right, thank you.
Yeah, sure.
Other questions for Alen?
And I don't see anything in the chat. So.
Okay, well, if not, I'd like to thank Alen for his very nice presentation, and Thierry also for the presentation that came before. Yeah,